Hello, my name is Daniel Miner, and I lead the practice for AI and data science for NTT Data in the DACH, that's Germany, Austria, and Switzerland region. I've been working as well on the topic of quantum computing for about 2.5 years now. And since this summer, I have been co-leading with my two colleagues the EMEAL Innovation Center for Quantum Computing. And with that, I'd like to hand it over to my colleague Christian Nietner, the head of quantum computing in the DACH region.
Daniel. Yes, my name is Christian Nietner and I'm head of quantum computing in NTT Data DACH. And I'm working in the field of quantum computing for the last 5 years and joined NTT Data in August last year when I took over the quantum computing topic from Daniel, who built it up. And I'm currently building up the quantum computing team and offering together with Alberto and Daniel in DACH and EMEAL. And with this, I'd like to hand over to my colleague Alberto.
Everybody, my name is Alberto Acuto from NTT Data Italy, where I'm responsible for technology strategy. And back in 2019, I've started the quantum computing practice together with Daniel. And now I'm head of quantum computing practice in Italy.
I'm going to start by talking a little bit about our collaborations and achievements in quantum computing. One of the 3 key values of NTT Data is teamwork. And I think that that's very important because a key part of our quantum strategy is teamwork, collaborations. We, as NTT Data, are not a quantum native company. We have been developing quantum expertise, and we believe in the power and promise of quantum computing. But as I said, we recognize that we are not a quantum native company. There is a lot of expertise in this field. We don't build our own hardware, with the exception of the coherent Ising machine from NTT Research. There are a lot of areas in which, in order to develop a full end-to-end quantum practice, we need assistance. And this is where our partner network comes in. As I mentioned, this is really key to our strategy. And in this sense, we have developed close relationships with various quantum native startups and scale-ups, with hardware providers, with various research institutions and universities around the world. And this exchange of information, expertise, and in some cases business, allows us to provide quantum solutions for our customers in a way that brings them and us forward. I'm going to talk about a specific configuration of this partnership now. We take what we like to call a triangle approach to the collaborations. We, as NTT Data, are the system integrators. We architect and integrate the quantum solutions for our customers. For some use cases as well, we may or may not do the algorithmic development. Our most important partner for the applied research side of this triangle is NTT Research, of course, our own group member. In addition to their general applied research, this also drives discussions of the quantum optimizer, the coherent Ising machine that they are designing and building. As well, we have 2 quantum native companies that we consider to be particularly strategic important partners. One of them is Classic. This is a company out of Israel that brings a high-level, low-code approach to quantum computing. We believe this is extremely important because the high-level software approach is critical for scaling of use cases. Most quantum algorithms, as they currently exist, are written in the equivalent of assembly, gate by gate, operation by operation. If we want to scale this out in the future, we need a higher level approach, and Classic is committed to providing this. One of our other key strategic partners in the quantum native arena is 1QBit. They are one of the oldest and most well-established quantum native companies on the market. They are from Canada, and they come with a wide range of deep algorithmic expertise in various areas of quantum computing. As well, they have their own partnerships with NTT Research. This configuration allows us to really cover the end-to-end quantum ecosystem. Again, just to re-summarize, us at NTT Data as the system integrators and solution providers, NTT Research and the other members of our research network as providing the basic research that we can transform into applied research, and companies like Classic and 1QBit that are supporting us with deep algorithmic expertise and innovative approaches to developing these quantum solutions. I'm going to talk now about one of our customer successes that we are most proud of. This was the BMW Quantum Challenge. The BMW Quantum Challenge was an open quantum hackathon in 2021 that was presented by BMW. It involved 4 real-world use cases from BMW's own industry experience. We decided to focus on one use case. In particular, this was test vehicle configuration. When a new vehicle goes on the market, it needs to be tested in many different configurations before it is allowed on the street, so to speak. These tests are numerous, and there are complex dependencies between all these various tests. Because many of them are physical tests, this involves the building and in some cases even the destruction of entire cars. This is obviously expensive and time consuming, and the optimization of this complex process can provide a significant business advantage. At the time of this, we were already in intense discussion over optimization problems with NTT Research and 1QBit, and decided that this was a perfect opportunity to really pool our resources and tackle such a problem head on. Bringing our industry experience and system integration experience, 1QBit's deep algorithmic expertise, especially in the field of algorithm hybridization, and NTT Research applied research, and as well their work on CIM, coherent Ising machine benchmarking, we developed for this challenge 2 different solutions. One of them is a post-NISQ that's I would say not a near-term, a somewhat more far future solution involving so-called gate-based quantum algorithms. I'm not going to focus much on that for the moment. And the second approach, which I think, at least from a strategic point of view, was really what drove the success of this, was a hybrid solver for this optimization problem. What does hybrid mean? Hybrid means that we have the latest in classical algorithm techniques working together with quantum techniques, a combination of classical and quantum computing together in order to generate the most out of both, where each can offer the most benefit. To briefly summarize that in a more technical way, this particular solution involved a hybrid meta-heuristic approach, which broke the problem down into small satisfiability problems, so-called SAT problems, with a hot swappable SAT solver. Quantum optimization solutions, such as the coherent Ising machine, D-Wave's quantum annealer, and other quantum-inspired solutions are particularly well suited to solving SAT problems, which means that when these systems are ready, we can plug these quantum solvers directly into the solution. And as well, for testing, for further development as well, we can use simply classical SAT solvers to address this. This future perspective and the scalability perspective is, I think, something that really contributed to our success. We won this use case category in the challenge, and that's led to our first paid customer engagement for quantum computing. So that was a paid proof of concept with BMW. And the discussions and the customer contacts that came out of that continue to bring us a lot of interesting opportunities to this day. To discuss our approach regarding customers such as BMW and many others, I'll be handing it over to our quantum lead in the DACH region, Christian.
Yes, when it comes to applying quantum computing technologies to the industry, sorry, Alberto, could you? Okay. When it comes to applying quantum computing technology to the industry and business challenges of our partners, we are mostly focusing on two application areas, namely quantum machine learning and combinatorial optimization. In these areas, we currently see our main expertise and have the strongest skills in our teams. Besides these application focus areas, we are hardware agnostic. Although NTT has developed its own quantum computing hardware, the so-called coherent Ising machine, which is a special purpose quantum computer for solving optimization problems, we make use of all the quantum computing platforms that are available and select basically the ones that are most suitable for the use cases under study. This includes gate-based quantum computers, quantum annealers, or our own coherent Ising machine, as well as quantum-inspired hardware, for example, the digital annealer by Fujitsu. To help our partners understand the impact of quantum technologies on their business and on their industries, we roughly follow 4 stages. First, we're using our knowledge, our expertise, and also our research networks, gathering together all the latest approaches and state-of-the-art algorithms, technologies. We help to identify with our partners the right topics and applications where quantum computing has the highest potential to improve or even disrupt existing conventional solutions. In the second stage, we implement these quantum algorithms for the use cases at hand and explore and analyze the technology advantage stemming from this new computing paradigm introduced by quantum technologies. Having identified a technology advantage, we map in the next stage the implemented solution to the respective business challenge, leading to a tangible business advantage for our partners and potentially allows to launch new services and products which include quantum technologies. However, since we are still in the so-called NISQ era of noisy intermediate scale quantum devices, so we are still very small technology platforms and they're error prone, so that limits our capabilities to fully build productive quantum solutions at the current stage. So this is still hard to achieve. And therefore, we also have the possibility, of course, to analyze and forecast when the development of a quantum solution can be used and which hardware requirements are needed to achieve that. Thereby, we give our partners a holistic understanding and an outlook on the impact of quantum computing on their business and enable them to lead their own quantum endeavors. And you see, in a summarized, so to say, this approach in a more structured way, we developed what we call the quantum computing leadership process model, where you see we start with analyzing and understanding the part about quantum technology. We call it quantum thinking, where we basically offer technology consulting, capability assessments, but also educations and trainings in order to raise awareness and educate our partners and their developers or subject matter experts. Followed by the exploration cycle, where we explore technologies and the technology advantage provided by a combination of different hardware platforms and software stacks. And having identified this technology advantage, we then map it to a business case to reach a quantum business advantage for our partners. The possible outcomes of this phase are implemented proof of concepts, technology assessments, and benchmark reports. And afterwards, we scale, or we help to scale the achieved insights and services internally and externally to put our partners in a position where they are in the lead of their own quantum journey, and preferably are able to launch new quantum products and services, which we would, of course, also support in building and launching and operating on quantum or hybrid, quantum hybrid platforms, or even just on conventional hardware and conventional platforms, but with the capability to be so-called quantum ready and be able to hot swap and change the underlying hardware platform to a quantum hardware if the requirements, the necessary requirements are met. So as NTT is very strongly committed to quantum technologies and want to help also the community to build up this new and exciting technology field, NTT not only develops its own quantum hardware to put into the mix, but also it actively supports on the software side of quantum computing. So in specific, we currently develop a cloud-based open source quantum development platform called Alchemy. And this platform is hardware and software framework agnostic to make use of a wide variety of state-of-the-art platforms, and includes our best practices and several decades of software development and operational experience from NTT. By this, we want to support our developers and, of course, the community, and pretty much help to democratize quantum technologies and make quantum technologies more accessible and easier to use for everybody interested out there. To summarize, Alchemy is built on a state-of-the-art software stack, making it very stable and easy to use and work with. And next to different quantum hardware and software frameworks that you can see here that are supported within Alchemy, it includes an algorithm library, a graphical circuit composer, a development workbench, and also supports continuous integration and continuous developments. The platform can make use of different conventional hardware components as well, like GPUs, CPUs, and FPGAs, allowing for a technology open development approach. The alpha phase of the service has been finished last year in 2022 and is currently under development to reach the public release phase. Now, my colleague Alberto will give you a more concrete insight into quantum computing applications in the next part.
Thank you, Christian. So we now describe our research use case, one of them at the EMEAL Innovation Center, the use of quantum reinforcement learning applied to smart robot operations. With the advancements in artificial intelligence, more software-based control solutions for robotic arms are emerging. Instead of hard coding the arm movement, its control policy could be obtained by learning. The most promising approach is reinforcement learning, whose goal is to define the best sequence of decisions, allowing an agent to solve a problem while maximizing a long-term reward. The set of coherent actions is learned through the interaction of the agent with an environment and through observation of rewards in every state. Deep reinforcement learning, the combination of deep learning and reinforcement learning, has emerged in robotic control as a promising approach for autonomously acquiring complex behaviors from low-level sensor observations. In general, using reinforcement learning for robot control is appealing because it can enable robots to move towards unstructured environment, to handle unknown objects, and to learn a state representation suitable for multiple tasks. Furthermore, in deep reinforcement learning, no predefined training data set is required, which ideally suits robotic manipulation and control tasks. So the agent and the environment are the main characters of reinforcement learning. The environment is the world that the agent lives in and interacts with. At every step of interaction, the agent makes an observation of the environment state and then decides on an action to take. The agent also gets a reward from the environment, a number telling it how good or bad the current world state is. The goal of the agent is to maximize its cumulative reward. So, through reinforcement learning, the agent can learn behaviors or policies to achieve its goal. Compared to reinforcement learning, deep reinforcement learning allows to fix critical issues related to the dimensionality and scalability of data in tasks with sparse reward signals, such as robotic manipulation and control tasks. However, despite recent improvements, the challenges in learning robust manipulation skills for robots with deep reinforcement learning are still far from being solved for real-world applications. This is mainly due to some well-known issues with deep reinforcement learning, such as exploration strategy and the slow learning speed, sometimes known as the curse of dimensionality. Quantum computing could solve such problems by reducing the learning speed and improving algorithm generalization. Two approaches are common in reinforcement learning. The value-based algorithms trying to find and approximate the optimal value function, which is a mapping between an action and the value, and policy-based algorithms, where the policy is defining an agent's behavior. The policy-based approach has its most suitable applications in continuous and stochastic environments, where faster convergence is guaranteed. On the other hand, value-based approaches are more sample efficient and steady. The approach we followed for robotic arm control is the so-called actor-critic algorithm, which basically merges together the policy-based and value-based approaches, combining their advantages. A robotic arm can be described as a chain of links that are moved by joints containing motors to change the link position and orientation. The figure shows the schematic diagram of a simple two-dimensional 4-joints robotic arm mounted and fixed on the first joint. The arm is able to move the links using the joints on the two-dimensional plane and can independently move each link clockwise or counterclockwise up to a given velocity. Last joint is referred to as the end effector. The robot arm task is then to reach a target point in the least number of movements. We created such environment using Box2D by adapting parts of the OpenAI GM environment called Acrobot. The core idea in the actor-critic approach is to split the model in two components: the actor, defining an action based on the state, and the critic, producing the state values. The actor essentially controls how the agent behaves by learning the optimal policy, and the critic evaluates the action by computing the value function. The training of the neural networks representing the actor and the critic is performed separately using gradient descent. As training proceeds, the actor learns to produce better actions to reach the goal, and the critic gets better at evaluating those actions. The actor-critic approach suffers from high sensitivity to the values of hyperparameters. To tackle with this problem and improve performance, stability, and proficiency, soft actor-critic has been proposed. This approach introduces multiple elements to the actor-critic approach: a large buffer memory to efficiently update the weights using the previous history, thus increasing learning stability. And the target neural network of the critic is introduced to further improve the stability and efficiency in learning the approximation of the value state. To update the target critic network, the soft function update procedure is used. Values include a factor to combine new and old weights obtained from the updated and previous steps. And to this purpose, a loss value of state and the loss of action must be defined. Quantum reinforcement learning integrates quantum computing and reinforcement learning. We used variational quantum algorithms, a hybrid computational proposed by to exploit NISQ devices to benefit from the performance boost expected from quantum technologies. The hybrid quantum classical approach may be the ideal setting to make universal approximation possible in quantum computers. A variational quantum algorithm workflow can be divided into 4 main components. The objective function that encodes the problem to be solved. The parameterized quantum circuit, whose parameters are tuned to minimize the objective function. The measurement scheme, which performs the basis changes and measurements needed to compute expectation values that are used to evaluate the objective. And the classical optimizer that minimizes the objective and proposes a new set of variational parameters. The quantum soft actor critic algorithm is quite similar to its classical counterpart, the only difference being the replacement of some neural networks layers with a variational quantum circuit, or VQC. There is a major issue when using VQCs, namely the difficulty to approximate nonlinear functions. In order to address it, 2 solutions have been used. First, data re-uploading, a technique where every VQC layer, except the last one, reapplies data encoding to have a more composite function expressiveness. And neural networks. Layers of neural networks are added before and after to leverage the high capacity of nonlinearity using activation functions. All tests have been conducted as classical simulations on digital hardware. Due to the simulation nature and the long time required to train this model, it was chosen not to explore how the introduction of noise may affect this kind of algorithm. In the first implementation explored in our work, only the actor neural network has been turned into a VQC. As we can see from the graph, both the classical algorithm and the hybrid quantum classical one behave identically when provided with the same number of parameters. They both can be trained to reach a behavior comparable to a deterministic benchmark. Note that this deterministic benchmark, that is the best possible number of movements to reach the target point, was made possible just because of the simplified nature of the problem. That is, it cannot scale to realistic scenarios. So, in the end, we could not detect any quantum advantages by just replacing the actor network with a quantum circuit. In a second implementation, all neural networks, the actor, the critic, and target critic, have been modified by replacing some hidden layers with a VQC. In this configuration, name it full QSAC, a quantum advantage was finally found. Indeed, a full quantum SAC with both actor and critic components leveraging variational quantum circuits exhibits a huge quantum advantage compared to its classical counterpart. Namely, it requires 100 times fewer learnable parameters to reach the same performance as the classical SAC model. Actually, a comparable neural network-based algorithm is one with the same number of parameters as the quantum algorithm, is not even able to converge to a successful robot training. This is the lower blue curve in the graph you can see. To recap, we observed a quantum advantage in simulating a quantum computer for reinforcement learning tasks. This advantage is expressed as a large reduction in the required parameters. The work has been published on arXiv and is now available for inspection to the global research community. The next steps involve two major streams: evaluate the effect of quantum noise and eventually test on a real quantum processor, and apply the problem to a real commercial robot arm using its digital twin for the training. Thanks for your attention.